of the potential. And now we're going to write the potential as a capital U rather than potential energy. Then we have the force in general as a negative gradient of the potential. So up here we have the force is equal to function of R, and so the potential must be a function of R as well. So the force is equal to minus the derivative of the potential, which is a function of R, straight to R.
We lost you.
Okay. And this is just general physics. So if there's a force, there's a potential. All right, so that's what we anticipate, or should anticipate. And I invite you to look at the very short 2 or 3 page notes that I posted on our website yesterday, I guess, about intellectual force and potential. Here I've just shown on the force axis and potential energy axis. This is potential energy U. The force that I drew before, and now taking the negative gradient potential, we can map out potential. And they look a lot alike, not my fault. So sometimes I'll draw a force curve and say we're talking about force. Sometimes I'll draw a potential curve. They look alike and not wrong. And you just have to know you talk about force now. One is the derivative of the other. Nice thing about the potential, this says that here is the lowest potential. So those molecules, if they had their druthers, they would be right at that distance apart. That's where they'd be. That's like pouring water in a trough. They would run down to the bottom of the trough. Here's another graph I made for a different purpose where I show them both in reduced notation. And we've got the force is red, the potential is blue, and something. All right. So now we're going to look beyond the ideal gas. We know we need to do that now because we know that it doesn't serve out in the real world. But before we do that, we're going to revisit the ideal gas to set the framework for how we're going to talk about these other models that we hope approach the behavior we've seen in that last curve a little better. So models of gases, we're doing talking about interpretations now. And I'm going to number these. Number one is just going to be the ideal gas again. We know all about it. But I want to emphasize some of the things we know about. Now I'm going to give us first time a genuine definition of ideal gas. Most people don't know how to define ideal gas. They just say P equal to RT. That's not the definition. That's part of it. So an ideal gas is a collection of non-interacting point masses. Ooh, that's important. Point masses. And the equation state P ideal, V ideal, motor ideal is P I is RT. And the force law, what's the force between non-interacting particles? Zero. How close together can they come? Infinitesimal force, right? No, there's no barrier. Here's the force law. That's it. There's zero. There's a line. See, that's like the compressibility factor line. This was on zero axis. Force, that was on the Z equal 1 axis. They're dull. That's what just don't find it all. So we've got the definition, we've got the force law, which is zero everywhere. It's zero from zero is equal less to r equal less than infinity. In other words, it is God. But the equation state V I is equal to R T. Now, let's look at some improvements. Here is some boilerplate. This is not part of our science, it's just some notation that I'm going to use, and so I will just stop and tell you about it. Some boilerplate or some vocabulary. Also, to facilitate comparison of the new models we're going to generate with the ideal gas, the ideal gas equation state I will write the new equation of state in this format. All right. All right, that's pressure of the gas plus delta P times the molar volume of the gas plus delta P is equal to RT. This is PI, VI is equal to RT if P plus delta P is PI, and V plus delta V is VI, of course. And so what are delta P and delta V? They're correction terms, if you like. I hate to use that word because these equations don't really correct it, but they're correction terms for the new equations to throw them into the ideal gas format. They're just written. So there's the boilerplate. Now we get back to some science. First step, first step in this process, part one. Ideal gas molecules have no force, hence they have no size. We've been taught from kindergarten that atoms and molecules have size. We've seen tabulations of them everywhere. So let's give our molecules some size. We think they all have some size. We'll give remember I told you early on, at this stage, we're playing God. This is imaginary stuff, and we can give it anything we want. We can say they look like little toy elephants. Give that size, whatever. Give them some size. Why don't we just do it the simplest way? What would that be? Shaped like an elephant?
Sphere.
Like an octopus?
Sphere.
Sphere, I like that. Bring it back to the sphere. Let's give a sphere. Now the simplest sphere that I think we could imagine is just a rigid sphere, hard sphere, impenetrable sphere. So let's let them be rigid sphere of diameter. I generally write this as sigma. Now, I have my show and tell here. I have some balls. Like that. Here they are, and they're sitting out here in space. Do they know about each other? No, because all they tell us is the size. They don't know whether they went around. They fly by one another and skim by a couple of actions separate. Do they know that? No, they don't know that. But they haven't bumped into one of them. They know it. They know it only when they are in contact. So we call this model, this is model number 2. We'll stop there. We'll do this in baby steps. We'll do this and we'll add some more steps on. Try and move it closer toward reality. So this model gas, is a collection. I don't have to write that out. Sure, I got that. Down here. And this is all in the lecture notes that are published on the web already. I sent them to you yesterday because today and tomorrow we'll be talking about that paper for that little work on beyond the ideal gas. So go there and read it. Just try to think about these things we say here. Model 2. A collection of non-attracting, no attraction, rigid spheres of diameter, sigma, and mass m. Force law. Well, how close together can they come? This is, they're in contact there. That's the closest they can get. This distance from here is a radius, that's sigma over 2. The distance from here is a radius, that's sigma over 2. So the distance approaches just a line. Universe. So put you on. So if R is greater than sigma, the force is 0. If R is less than sigma, the force is, it can't be less than sigma. I say, I draw this up to infinity, it doesn't have to go to infinity. If I drew it as a potential, it still didn't look the same way. It goes to infinity there at sigma. Like this wall. You hit this wall, if I hit it, a molecule comes in and it hits it with a force of 1 Newton, then it pushes back with 1 Newton. If it force 1,000 newtons, it pushes back with 1,000 newtons. So on. This finally is rigid. That's the size. Ah, that's all right. So what are we going to say about this one? Well, it's B plus delta B times V minus delta B is equal to RT delta B. Anybody guess what that's going to be? Now the pressure that the wall is getting on here is from the impacts the molecules making. Okay? We know the flux of molecules on there. Now it's just gamma in. It's the number density times the average speed perpendicular to the wall. We calculated that the other day. So by giving the molecules some sign out here, is that going to change the rate of what they're banging on the wall here? Giving the molecules some sign, is that going to change the velocity distribution? Delta is going to be 0. Now, how about delta V? What the hell is that? this case, it's pretty easy for us to write it down, at least at modest, low to modest densities. If the pressure's not too high, what will nearly all the collisions be like? They'll involve two molecules. Probability of three of them colliding simultaneously at the same instant in time is very low. So we just have to look at bimolecular collisions to get an idea of this. Now, and I have my show and tell here, I could really show you some good stuff about this. You have to imagine, I have these hard objects, bring them together, and if they didn't have a size, the centers I could bring right up to 0. They were point masses. I could bring those centers right essentially together. Here I can. There's some volume excluded for the free motion of the molecules due to the collision. And I think of this, if this one, let's say, is trying to get into the space here, there's another sphere that its center can't penetrate. You see that? All right. That's nice. We'll get to that a little later. Diagrams are here. But, so just now, let's say that free volume for molecular motion is less than the volume of the gas. And that expresses itself when the molecules collide. So all we say is that the ideal volume, which is the volume plus delta V, is less than the volume of gas. Therefore, delta V has a negative line. I'm going to take the pressure, subtract off some volume because of the excluded volume for free motion. So we have then the equation state is pressure plus delta V, volume plus pressure delta V, volume plus delta V, sigma RP, that's P plus 0 times V minus something, and I call that something B. I don't, that involves B. We're borrowing again ahead of spot B, and that's equal to RT, and B is equal to the excluded volume for free movement due to collisions. It's the free excluded volume, I should say, per mole. Alright, so that's what it is. So we have the equation state for that case, and it's just P, V minus V And, we can show from that, that the, compressibility factor, which is V over RT, is equal to, V over V minus V. And, so this is a little less than one. Equal greater than one. Equal greater than one. So this, causes the compressibility factor to rise up from value. Yes. Value. I include this exercise not because it's particularly important, it's just a bridge to the next step. If you were studying gases at very high temperatures, like in the atmospheres of stars, it would be much better than the ideal gas, because the partial, this spoke up high at high densities and high temperatures. All right, let's go on beyond this. Model 3. Here it is. What's the next thing we're going to do? Give the molecule some softness. Sure, we don't think molecules are good in little hard infinite spheres. We know they're not. We know they're not because of this, our expectations over here. Prove that graph. We know that for realistic or potential, that this doesn't go straight up, it goes up steeply. And that's because of some compressibility. So that we've got to allow our molecules to squeeze together. Instead of me banging two steel balls together, I'm banging two tennis balls together, or Nerf balls together. So the harder you bang them, the more they squeeze in. So how are we going to do that in this next model? Well, we do that, model 3, definition, collection of non-attracting soft spheres of diameter, sigma, and mass m. The force law is much the same, except that R is smaller than sigma. Here's sigma, where they just touch. Instead of going straight up, it goes up above negative sign. The details of it are important at this juncture. It's all we've done, given us the negative slope. And it's pretty easy to see what happens. When we do that, we find that P plus delta P times V plus delta V equal RT. Now what's delta P going to be? Giving those same softness, is that going to change anything I said about how hard the molecule is hitting the wall over here? How frequently? No. It's not going to affect this. This is 0. What's this one going to be? Well, it's still going to be something negative. But instead of saying it's a constant, what can we do? Assume that delta V is some function of the temperature, flight temperature, because kinetic energy proportional to temperature, change how hard molecules bang into one another. How hard they bang into one another determines how much they squeeze when how close together they get. So let's call that V of P. And then our equation statement becomes P times V minus V, a function is Z is equal to PV over RT, and that is just equal to V over V minus V of T. And that is still everywhere greater than equal to zero. Okay, so we've taken care of we've taken care of this part of our expected behavior, and we've ignored this one down here in this fraction. So what do you suppose the next step is? The next step is to give our molecules some long-range attraction.